want to make a case for the language just as a quick show of hands to kind of get like a level set of experience and just kind of variety of experience. Who here has programmed anything Crystal? Okay, that's kind of what I expected. Java, C, and or C++. Okay, and then Python, Ruby, JavaScript, those kind of interpreter languages. Okay, cool. All right, it's a pretty good mix, but all right. So this is going to be a case for the language. It's going to be less about like the flow control and the syntax of how to make a proc or a lambda, things like that. I want to kind of talk about where we've come from as an industry and kind of where we're going and why I think certain languages are going to be a fit for the next kind of set of languages to become popular and stuff like that. Real quick, my name is Jack Thorne. I'm a senior software engineer at Alego Energy. It is an energy startup in Chicago. We're actually pretty close to here. We're like one of the only tech companies not hiring right now. We're going to be hiring for next year, but that's a little ways away. I am 123 on the internet, or 123, and this is some contact info in case you want to get a hold of me afterwards. And also, if you are interested in Crystal and you go to the GitHub repo, you'll see like the Gitter and the chats and stuff like that. Usually, you can contact me through there too if you want like an IM-based kind of chat. So, real quick, we're going to go over a little bit of compiler history. This is going to be super brief and hopefully pretty entertaining. I was not around in the 70s or the 80s and I wasn't programming, so a lot of this has come from conversations that I've had with my professors or reading a little bit and trying to catch up on that and seeing kind of the overall view of where we've been and where we're going. Some quick terminology because not everyone knows about compilers. There's a front end, there's an optimizer, and then there's back end. We'll probably talk a little bit, we're going to talk mostly about the front ends of compilers in kind of some later slides, but just so you understand kind of some of the terminology and how it works. Real quick, hardware vendors started distributing hardware and they distributed with assembly of their own instruction sets. And as hardware vendors wanted to have easier onboarding to their hardware, they kind of wanted to create like the Rails or easy APIs that get up and running on a piece of hardware. They started distributing compilers along with their hardware. They kind of had to choose a language in some sense of like what is the easiest way for people to come on at that time. So they wanted something really high level at that time. So a lot of them chose C. C became kind of a lingua franca, like both from a mix of compiler like releases, but also just popularity. And everyone wrote their own compiler, which meant that C kind of varied drastically from platform to platform. From people I've spoken with, C is a very kind of fuzzy spec. And so at that point, C just kind of was like bananas, depending on what compiler you're using on what hardware set, it could interact differently. But if you use C, you can kind of write anywhere. After that, operating systems and kind of big vendors stepped into the space and started distributing compilers. You were really bound to the operating system itself. And because of the feature sets they would release, your code became less and less portable. It became less of a write somewhere, write C, write portion or something, distribute it on someone else's kind of hardware. Some examples that came up when I gave this talk before were something called pinvoke or other things that were on the Microsoft compiler MSVC, I believe. And like they thought it was amazing. You could interact with all these different types of DLLs and all these different types of things, but you could only do it on Microsoft. And so they generally tend to have poor optimizations over time. They were very opinionated in design and they focused specifically on certain operating systems. And out of these needs and out of other needs, Richard Stallman came in and decided to do some open source work. He quit his job at MIT and said, I'm going to open source all the things. And he wanted to open source something called Herd. I mean, he wanted to open source many things. He was very fixated on open sourcing a Unix-like environment. He wanted to write all this code and give it out to the world. But to write code, he needed a compiler. So in some ways, GCC is a giant gap shape to be able to get like what he wants done. And I'm a little oversimplifying a lot of that, but the point being is that he had a lot of other goals, and he used the examples of compilers that came before him, and kind of released his own. There was a few design decisions and just other things that came about from that, from those incentives. One of them was that the compiler was pretty monolithic. It was pretty integrated. A lot of things were just kind of all baked in with each other. There wasn't really clear separations. It was a kind of a means to an end. It was a very, it was a very purpose-built piece of software. And you got a lot of the benefits of open source from it, though. So, anyone could modify it, anyone could extend it, anyone could use it and create enhancements for the C language itself. The thing is that if you want to write something other than C, you're like, I want to make, this crazy language called Ruby or whatever. GCC would be like, well, we have C and we have C templates. So you can do C or C++. That's kind of like your choices. I talked about a little bit of this, but the front ends were super limited. If you wanted to, for example, write Crystal, which is the language we're going to talk about, back in, the 90s, it wasn't an integration, there wasn't the hooks, there wasn't the kind of the APIs or the libraries to even design a language like that. And it was a real big kind of hindrance for a lot of concepts that were coming out at that time. Some of the things that we really wanted to kind of move towards were more managed environments. OO was becoming very popular. And there was just a lot of reliability and consistency problems with some of the software at the time. They wanted to get rid of things like C-style strings. They wanted to, eliminate use after free errors. There was a lot of kind of trouble with kind of problems that the languages at the time were presenting, and people felt like they had better solutions for that. They wanted to create things like Python or Java or things like that. So we moved to kind of like more of the virtual machines, the managed environments, those types of things. There's a lot of reasons why these became more and more prevalent, including runtime environments, but we wanted the management over the environment itself that the code was executing it at runtime. We want to implement a lot of features that weren't in compilers. A lot of the features that we can have in compilers today, there wasn't really a tool set or a way to build them. A lot of these features were implemented kind of holistically inside compilers themselves. Python wanted like a lot of different kind of like the dicts and lists and all these types of things. We wanted to add a lot of structure and a lot of things that people were re-implementing all the time and create them inside safe environments, stuff like that. Some of the trade-offs were they became way less effective or efficient implementations. Their implementations were a lot slower. They were not capable of doing certain things. You just weren't able to fundamentally do certain things on platforms or computers in general. So they weren't able to manipulate some things at like bytes or binary levels without digging down in the C. They weren't able to do kind of a little bit more like memory-esque type stuff. And as these virtual machines were built, compilers became better and better and started adopting features from hardware vendors and bringing them up through their entire tool chain. And if you have a 10,000 line interpreter project or larger, you have to integrate those features that a compiler could give you throughout your entire code base. And depending on what you've done, that could be nearly impossible, or could just take a long time. It took a very long time for some of the more massive projects like Java to adopt 64-bit or things like that. One, because compilers didn't have 64-bit or other types of things. It was really hard to integrate them into the entire projects themselves. So this is the greatest hits of kind of this era. These are late 80s, I believe was GCC's introduction. Early 90s to mid 90s was really a crest of popularity. When going to the Wikipedia pages, all of these were originally released in GCC. I wasn't there when they were released, and this was a move to safety, OO, VMs, managed environments, and I actually think this is probably one of the greater kind of boosts in productivity in the industry. I think moving especially to managed memory, which happened before this, but this is like the real introduction into the mainstream programming industry. And when we stopped having to worry about managing memory, I think it was a massive, massive productivity boost. And one of the things is that we did get a decrement in, regression in performance for programs. But I think it was, in general, I think a lot of us who program Ruby, which I saw quite a few hands for, would agree that the increase in productivity in writing in Ruby is worth the not managing memory in a C or C++ style environment. So this was a giant step forward, and these were kind of the environments and the languages that came out, and they provide a lot of safety. We don't have to worry about use after free, someone going out of the memory of a string and capturing something they shouldn't have to be, kind of all the security bugs of Heartbleed to all the frustrations of memory leaks. We've kind of gotten rid of a lot of those with these type of languages. You can always cause memory leak, but we're far beyond where we were before. So just a quick look into Java as an example. I always joke that Java is managed C++. It specifically manages memory more, but it takes a lot of ideas and kind of puts them on a VM, puts a lot of safety around them, and a lot of assurances. It was OO, and there are some LLVM targets for JVM environments. I think Java 1.0 could probably be implemented in the current version of LLVM, but just to show kind of how far we've come from compiler technologies to GCC kind of having no ability to even write a front end at that time, to now being able to completely implement a soup to nuts language, look kind of where it started from. So that's kind of the difference in where we are and where we were. And the write once, run anywhere, I think this is kind of like a double-edged sword. This was definitely a mantra of Java at the time. Compilers definitely are like you write it and it will build on any machine. Like that's kind of one of the features of compilers. You write it once and it has the backend targets. You can run it anywhere. The thing is that compilers don't come with the understanding of operating systems, of different environments, of a lot of different things. So what Java, I think, really showed us is the write once to an API that's like a file API. And then that file API will work on Windows, it will work on Mac, it will work on all these environments. So it is, I'm not saying that that was a feature of the compiler, not a feature of Java, but I think that part of it was definitely kind of something that compilers did, and part of it was creating abstractions that were abstracting away deployment environments and execution environments. And I think that we've carried that forward in other languages today. And Crystal's had a really interesting discussion on the Windows platform about whether or not, file descriptors should be exposed in any part of the public API because they don't exist on Windows. Should it be duplicated as an implementation on Windows? Kind of a lot of different interesting, discussions about how to make languages that can compile down to target not only hardware like x86, but also target execution environments. So I think we learned a lot about that in this kind of era. And I think it was 2004, LLVM was released. It kind of, I've listened to a few of the different founders of LLVM explain their kind of a purpose for the project and stuff like that, and they vary a little bit, but I think most of them have stated that it is a research project at the time for dynamic and statically typed languages. That was their concept and that was the project. The output of that idea was a compiler. So, the idea was we want to research dynamically and statically typed languages, specifically compiled. They wrote a C compiler. And a lot of this was kind of ripping apart and putting back together, reassembling parts of languages. And to do that, they built a lot of different libraries and they kind of centralized on this thing called IR, internal representation. They were not the first to write an IR, but they were the first to kind of marshal and serialize it to like a file, and they were the first to not have it just be in memory and be something that a lot of different things could operate over. And the modularity plus kind of an API of IR and creating different front ends and having this be a project that's very inquisitive and introspective created kind of this toolkit for languages themselves. And they had, clean separation components. You can read the bullet points on the slide, but yeah. So from this, we actually got much different languages today. These are all built on the LLVM. Swift is interesting. The first commit on Swift was 2014. It was released in 2014 production. So the bootstrapping of the language, and Swift is a notable exception from other languages in that they could deploy to like millions of devices as soon as they hit like the run, as soon as they hit like the production push button. But they've been talking about this for a lot longer before they actually committed code apparently. So this has been a discussion in Apple for a while of what's next. But they were able to implement it quite quickly, probably because a ton of LLVM devs worked it out. So they all knew, how to write a compiler. They all knew how to write, they had written multiple front ends. They were the ones who wrote the C++ front end, the Objective-C front, like they built all the tooling around it. So they understood it quite well. But the ability to take a language, or something that would be like Java or something like that, be able to have the richness of feature set, the richness of ecosystem, and just drop something in the environment, have it all work, was kind of bananas. And I think shows a lot of the power of these language ecosystems. They're not just compilers. They get everything from performance tooling, they get debugging information, they get just everything that comes with an LLVM toolkit as soon as you build it and deploy it. All of the code completion types, the Xcode, people love it, hate it, but a lot of the tooling that Xcode basically worked out of the box with Swift. And that was pretty bananas. There's notable exceptions as to which tools didn't work. But other languages like Rust and Julia have been pretty popular on the scene. They came out a few years after the LLVM kind of became fully open source in the community. They are, I think Rust is really interesting, and it shows kind of the variety of languages you can build on the LLVM platform where their target is not the same target as Swift. They want provability, kind of parallelism and concurrency at runtime. And the ideas that embody Rust and Swift are very different. And so you don't always get the same things on the other end of the LLVM, but you are able to just kind of build an entire language soup to nuts, much quicker than you could before. Kotlin has some targets for the LLVM. It's kind of an example of other things you can do on the platform as well, but it's becoming quite popular. Most people run the JVM. And there's also Crystal, which we're kind of get into a little bit more here. But I want to first talk about kind of why I think that these languages represent like the future direction of language development. I think that we learned a ton in the era of VM languages. I think we learned a ton in compiled languages. I think if you were to take the two biggest boosts in productivity in the software industry as a whole, it was going from handwritten code to compiled code, and then it was going from managed memory from unmanaged memory to managed memory. And some of that we had to do with compilers, compiled code, and some of that we did with VMs. But I think as language toolkits like LLVM, and even what's happening in GCC these days, we're seeing that kind of collapse back down to the compiler, and we're able to get a lot of advantages in the compiler ecosystem and kind of, like not absorb all the disadvantages of VMs, if that's a good way to put it. But we're getting kind of a lot of the advanced semantics and stuff like that. You can build quite well. You get provability, you get reliability, you get performance. There's a lot of things that the compiler does for you. And then you get integrations. So there's hooks now to LLVM. There's really easy plug and play kind of garbage collectors and stuff like that. There's even like tutorials of writing your own language in LLVM that include how to just plug and play a garbage collector. It's pretty cool. You get a lot of modularity, and you get cross-language support, which is a really horrible way for saying if someone makes an advancement in any part of LLVM, everyone gets the benefits. So one of my favorite kind of features that we implemented in Crystal was thin TLO, which is link time optimization, and that's an LLVM component, and everyone gets that. Rust gets that, Crystal gets that, everyone gets that. So it is pretty cool to see people doing advancements in compilers, and then having everyone in the ecosystem automatically get those changes. We're implementing 128-bit numbers or integer support in Crystal, and if you were to say like how long would it take to do 128-bit like support in Java in the 90s or something like that, it's a much different question. You're able to take a lot of the kind of the tool sets that are inside the ecosystems and just kind of, if you can integrate with a C API and your parser and semantics can understand it, your language can have it. And so that really provides a lot of very big advantages, and you can kind of reuse a lot of other people's work. So it's pretty cool. So let's talk a little about Crystal. Crystal is definitely newer to the scenes. It is not 1.0 yet, for those of you concerned about that. I think that it is very much production ready, and there's some people who have released production apps for it. There's two specific targets that they don't have, just quickly, is before 1.0, they want to have full Windows support. You can build Crystal on Windows, and you can run it on Windows. There are still some parts of the Windows API that they're trying to make sure are completely cross-compatible, that they work as expected, and things like that. So that's still kind of get some of the bugs out of Windows part. And then they want full parallelism, and in Crystal we'll talk about that a little bit more. But it's roughly where Ruby is for concurrency parallelism. So. Yeah.
Who is building Crystal? Is it like a company that's building it to use it, or is it just a group of people that are like, is it things that we think would be better in the language?
Yeah. So Crystal, its original core team was from Mantis, which was a consultancy, and it has grown out from there. None of the original founders of the language actually work for the original consultancy that it was birthed at, and right now it's a community managed and maintained project. So yeah, this is actually a really interesting side note. I'm thoroughly attracted to projects that aren't controlled by corporations, and I think that's a kind of something as a dev community you either kind of are attracted to or are not, whether or not you believe that a corporation will have the support in your best interest in mind long term, or whether or not you believe the community is. I personally am strongly in bent of having communities control their projects. It's one of the reasons why I'm attracted to Crystal. So if that's something that you also are attracted to or believe in, that is it's a really big benefit of Crystal. So kind of diving in the language, it has a few goals. Its tagline is fast as C, slick as Ruby. The fastest C is as fast as LLVM can kind of deliver. I mean, there is a GC in there. and you do get some stuff, but it's basically leveraging all of the kind of optimizations and advantages that you can get from a fully compiled language. Slick as Ruby, I think, is a kind of harder one to kind of nail down. The way I think about this is just abstractions. We don't want to write vectors or, the implementation of a hash or things like that again. So it's providing kind of high-level abstractions. One of the really nice parts about Crystal is that it's super easy to write C or anything else in Crystal, so that abstraction layer, you can pierce to whatever depth you want. You can use a lot of the higher-level primitives, the higher-level constructions, and the higher-level abstractions that they're going to give you. But if you really want to, you can go straight down to the bits in Crystal and really do some super fun things. I wrote a SOX 5 proxy in Crystal, and you can, putting literal the byte class and just mapping it over an array or things like that is just so easy. It's really interesting to see kind of what levels you can write things in Crystal and how the abstractions can be beneficial at a high level, and what type of granularity you can get. I think that you get all the predictability, efficiency of compilers, and you get a lot of the practicality, the kind of advantages that we've seen, the kind of speed gains we've got not managed memory, not managing other abstractions. They kind of are trying to get both of those advantages there. The syntax is pretty modern. They have, the implicit parentheses where you don't have to put them in. They have implicit returns. They actually have these kind of cool features. This is one of my favorites, where you can actually assign instance variables inside the function definition, so you don't actually have to write, this equals this and give them different names and stuff like that. It'll just automatically assign them for if you put instance variables in there. It's got a lot of the no semicolons needed if you don't want them. This is the syntax for adding types, and obviously you don't have to add types everywhere, so it's going to do a lot of type inference. This is just kind of a example of a lot of the different types and features of syntax inside Crystal. There are a lot more features, but in general, they strive to take a lot of the things they learned from Go, a lot of things that we learned from Ruby, JavaScript, whatever, and incorporate them as seamlessly as they can in the language to make it as easy and as kind of modern, flexible to work in. It's very Ruby-inspired syntax, where you have the def and ends. There's a lot of ends. If you like kind of the brackets and other things, that's not a part of this, but they do try to strive to make it as easy as possible for that. And it's the C-style family, where it's not the derivative of ML or other things like that. But that's just kind of a generic kind of take on the syntax. I actually really like the syntax, and there's a fair amount of both the compiler and projects that will do auto code formatting and other things for you. And because it's a compiled language, they can do a lot of really cool things for formatting. Yeah, if you're into that, you like Go FMT, things like that. There's a lot of kind of support for that in this language. It is object-oriented. For those that like the object-oriented style, everything's an object, and it's firmly built in that paradigm. It does have a lot of functional inspiration. There are iterators and enumerables. There are a fair amount of, they have recursive types, so you can create a lot of recursive kind of anonymous functions and things like that, and you don't have to put all the types in. It will automatically figure out typing recursively throughout a lot of different kind of crazy functions and other things that you can write. So that's pretty cool. They've made sure that they haven't kind of locked themselves out of introducing any kind of functional features, but they're definitely primarily an OO language. The error handling, I think, is kind of where a lot of the industry and a lot of previous languages have kind of fallen on, with kind of the throw catch style. You have to begin rescue, things like that. Just as an example of kind of other things, because I feel like this is so common in our industry, is something like Go, where you have to set two variables and return them and then check them on the other side and stuff like that for some error catching, but they follow a very kind of, I would say, the mainstream approach to that type of flow. So this is a really interesting part of Crystal. You have the static type checking. This is what provides a lot of the advantages of the compiler. It's what reduces a lot of errors. And I have come from a dynamic language background mostly. Most of my work is in Ruby, but I've also done things like Python and stuff like that. And I, firmly fell into that camp. And I have to say that I write Crystal like I write Ruby. And I don't put types in, and it all works. But even by not putting types in, I have saved myself so much pain in production. I have changed things in things that in projects I have running in the wild and 3 files over, it wouldn't compile saying this does not respond to this call or things like that. So even though you have tons of flexibility, you don't have to write things in, or maybe a nil will flow throughout most of your program, and it just doesn't matter because when it returns from the HTTP response, whatever, it's just gonna be a string or something like that. When it does actually catch things, it is so nice, and you really do get a lot of things that are not delivered to production from kind of its type checker. I think it's a great balance of having all the advantages of like type inference and things like that, and then and also catching kind of your errors. It's really it's taken a lot of the languages that have come out in the past 10 years and kind of tried to learn from them and learn from their type systems and what they've implemented. It does have type inference. You do not have to put types down. It does have union types, so it will either automatically detect, or if you put many types inside a signature, it will just collapse them all or check them all kind of in wherever they're being called. This is an example of having a person with a greet and then an employee that inherits from person, and check. They will know if you pass it a string that it should call this, and if you pass it int, it should call this, and if you pass it true, it will just break. So this is a kind of example of both inherency and then also that kind of stuff. Yeah, it's globally scoped. This is something that's come up a few times. Unlike Go, they've decided to make some convenience trade-offs, and that means that the compilation is both a little slower, but one of the bigger drawbacks is that it does have a limitation kind of the growth of a project. There are 20,000 line projects that compile in 3 seconds, so they aren't really hitting those kind of limitations yet. But if you want to write like Google and you want to have the whole infrastructure on it, you're not going to probably be able to run a million classifiers or something like that. But I don't think it's a problem for most people, but because it has come up in previous discussions, I wanted to at least let people know that there is a limitation on there, but I've never hit it, and I don't know no Crystal project that's hit it yet. So yeah, that's a little bit about the static type checking. Is there any questions regarding this? Because this is kind of a lot of different disparate topics. Okay.
You're going to show union types, Mark?
Yeah, union types. They're both from the type inference, like the compiler itself will infer union types, but it basically means that something like the message could be like an int or a symbol, and you can actually denote that with a bracket. So it will basically just say it could be this, or there's a lot of kind of syntax sugar. You can do int with a question mark, and that will just say int or nil. So it kind of allows nils to be easily put inside the syntax and kind of the API. That will mean that for example, if this was int or bool, this would not show an error when it compiles. This would allow that to be interpolated in the string, basically. So it's a way of allowing many types to kind of be passed into a single function call, or just be used inside a procedure in general. It will check to make sure every type that is that variable can actually respond to all the calls that it will that is called in. So like if you have a bunch of different things here and it will return or not get there, if the compiler doesn't know that, it's going to say something down here can't respond to 2s because it's nil or whatever. Like it's gonna check every part of that variable and every part of your function and make sure that all the calls on that can be done, which is one of the reasons why changing something and then having that be used 3 files over, even if you don't put the type in, even if you don't say returns user object, as long as everything else down the chain of that responds to or has something that nil can respond to, it will all just work anyways. So that's kind of a little bit of how that works. Also, with type inference and union types, specifically union types, if you eliminate part of the type, the compiler generally can figure that out. So if you say if user, that means that the user is not nil. So it'll actually remove nil from the union types inside that block and make sure that everything that responds every time that variable is used, it will kind of remove nil from that check. I can give kind of more examples on that in the union typing and also kind of the scoping and stuff, because I think it's easier to see that than it is to kind of explain it. But the union types is just basically saying that, all of this variable can be many of these types, and as long as it responds to that, it will compile. So is that kind of a little bit better?
Yeah, I was wondering if pattern matching is why I was bringing it up.
Oh, pattern matching. Not in the Elixir sense. Okay, so it won't do that in that way. But yeah.
If you had a method with different arity, would that work?
Yes. Yeah. When you have methods with multiple areas, the compiler actually just iterates through every possible arity, and then because it knows everything that calls it. So when you actually do that, you'll see, especially if you throw an error, you'll see like greetings or whatever for greet, and then you'll see all the signatures that could possibly be depending on the rest of your code base. So it kind of it's pretty cool that way, but it takes the multi-arity kind of dynamicy and reduces it down to a literal call.
So like if I define multiple times greet, def greet, multiple times with different signatures, that would be like an equivalent of like pattern matching in a sense. Would that work?
Yeah, I guess the pattern matching that I'm associating is that you can put multiple bind variables with underscores, and then it will like associate them back. It doesn't do like that syntax-wise, but it does do the pattern matching in the sense that it will match all of the types going into a function. So yeah, I guess pattern matching might be a little bit of an overload term, but yeah, exactly. It will pattern match which function you want to call. It also does overloading. So Ruby doesn't do that super well at all. But you can do overloading. It does native code generation. This is probably not super commonly used for most people. I don't think most projects are going to be like, does it have native code generation? But it is really great for that tooling ecosystem. I spoke earlier about how Swift was able to plug in almost all of Xcode. It got debugging, it got performance stuff, it got all this type of stuff from the language and from the entire ecosystem that was built out before it. You kind of get all of that with Crystal. I have used the Xcode. It was actually for like the iPhone profile debugger and stuff like that, just to see how it works. You can grab symbols off of certain stuff. I don't really understand part of the Xcode tooling ecosystem, but it was pretty cool to like type in a symbol and then like see every time it was used and see kind of all the stuff inside the what took the most CPU, the most memory, stuff like that. So basically, any part of the tooling ecosystem you get. I have actually used native code to lose an argument. I thought I was winning on GitHub. So it is really cool because it is a source of truth. If there was a thing where I thought two things were compiling down to something different, and you can create a simple program that has those two things. And the benchmarks might be different because of the way computers execute code and stuff like that. But when you can see the exact same instruction sets, you're like, oh, well. In the end, the compiler spits those out the exact same. So it is kind of interesting in that you're not dealing with a VM where some things can be unknowable, unpredictable, or really hard to measure. Like in the end, this is all going to boil down to assembly, and you can look at the instruction sets and be like, this is literally what's happening, and that's pretty cool. Yeah, this is just a simple. This one is for Linux. This one is if you're on Mac OS, and they have really nice debugging stuff where you can see the signatures of certain. So you can just part of the release are going to become fully parallel, but right now the multi-threaded support is about the same as Ruby, where it does IO parallel and it does everything else basically concurrent. There are some other things that does parallel, but IO is the big one. It more has the channel kind of spawn type syntax. I guess it uses fibers, so it has kind of that Ruby-esque type thing where you can use fibers and stuff like that. But it has what I perceive to be more of a Go style, where there's a lot more use of channels. There's a lot more use of spawns. The standard library does things like that. Their documentation does things like that. They're kind of pushing more towards that model. There are threads if you really want to go the advanced style and you feel like you need concurrency. There are a few projects that have used them. They are private APIs until the multi-thread scheduler comes out. So they are not exposing documentation, but if you really need concurrency, I've done a few things in there and I've seen people do it and it works fine, but it's definitely private. It's Ruby-like concurrency, so right now that's its deployed state, which works quite well. There's some people there are both a ton of benchmarks because people have been benchmarking Crystal throughout its development, but there are also some applications that people have really tried to stress to see if how much the small Heroku dynos and stuff can take, and they can take a ton. They're actually Crystal is pretty good for web servers as well. Meta programming. I was surprised at how much some people dislike this and how much some people like this. I'm a fan of open classes, but they, in many ways, they've adopted a lot of their meta programming and kind of dynamicy from the Ruby kind of mindsets or the Ruby philosophies. There are open classes. The community itself is a lot of ex-Rubyers, or current Rubyers, so they do not use open classes lightly. There are not a whole lot of libraries I've seen in the wild that reopen nil or things like that. There's no .blank, there's no .present. They aren't monkey patching object. So I'd say that in a lot of ways it's pretty responsible from a community sense, but also from the standard library, they do not, they don't use certain things with open classes where if you require some parts of the standard library, it will monkey patch an object. It's pretty much use open classes, and some of the more crazy parts of meta programming more conservatively, but when they are there, they work quite well. They have method missing. They have defined methods. They have a lot of this, their meta programming is done in a macro style syntax. So it is a little different than the rest of Ruby. You'll see kind of these brackets here, this ID, some other stuff. So this is it kind of adds a superset onto the Crystal syntax if you start to get into more of the meta programming. All the meta programming is done at compile time. So there is no runtime environment in which you can start modifying the program itself. So if you want to take a web request and take like a JSON key and define a method on an object, know that you can't take dynamic input and create code paths off it. The only time, the meta programming is only at compile time. You're directly manipulating the AST, so it's not gonna have the same level of dynamic stuff that programming languages like Ruby have. But as you can see from this, you can method missing. The mashup is not actually on class foo, and you can pass it stuff, and then it will take all the args and join them with a pipe, and you can get something fun out of that. So it does do a lot of kind of more dynamic stuff. There are a ton of DSLs in Crystal. People have been making a lot of libraries for web frameworks. They're making a lot of libraries for ORMs, things like that, and they're pretty seamless in kind of their usage. So you definitely go over a few examples of that in the wild, but it's pretty powerful. So standard library. I find the standard library to be pretty. Oh, go ahead. Sorry.
Yes. With the method missing, how does that work in terms of type checking? Like if you define will the compiler tell me that I can call mashup on foo? How does it know that mashup is valid and what arguments it takes?
Yeah. So I have not actually checked how the compiler does it, but this is from my understanding. From my understanding, when it compiles and it finds that it doesn't have a function call that exists on a class, it will check if method missing basically responds to that or if that signature matches, and then we'll try to compile that in place. So it's basically method missing is a special case in the compiler for compile time, where if you just call something inside a controller or inside a different object, it will check to see if you've even defined this. And if you have defined this, will it actually work with what's called?
It looks like some of the syntax inside method missing is similar to the macro definition. Am I reading that correctly? Where you have the double parens or double brackets or something?
Yeah, so this is actually a macro. So that is everything inside method missing is basically a macro. You can not use that, but you're not going to get any of the advantages of being able to use the inputs. So you do a method missing that just puts I don't know what you're doing, but if you want to use the args coming in, you have to dip down in the macro syntax.
Oh, okay, so that eventually generates code that the compiler can type check in some sense?
Yeah. So macros are basically two passes. They generate Crystal code and then they compile it. So yeah. The macros as well are a little different. You'll notice that this says .id at the end and things like that. There's going to be it's kind of a DSL around. It's like both Crystal because you're output in Crystal, but then it's also a DSL around the AST. So there's they have docs and guides through it, but its API is a little different. And when I first adopted it, I thought it was going to be exactly like Ruby or exactly like Crystal, and there are some differences, but so.
But based on how you use that API, the compiler can infer how you're using the arguments and therefore what signatures are valid.
Good. Yep. So standard library, I find this to be a pretty soup to nuts library. I find that it even has things I don't see in other.
What is the relevance of the link graffiti?
I just, when I put presentations together, I don't like I don't really think the memes and stuff look as good as kind of street art. So I just kind of grab things that look cool. I don't really I find things that kind of feel like they fit whatever theme it is, but in general, I just kind of put things in there that I think make my slides look better. So it doesn't have a specific link is not specifically associated with the standard library.
Okay, that makes sense.
I find the standard library to be pretty soup to nuts. It's definitely batteries included in a lot of ways. I don't find many standard libraries that have Markdown and kind of some of the other zip and other things kind of included. Most of them includes it these days, but there's definitely crypto and OAuth, and there's kind of a lot of stuff in there if you're looking for it. And it's not a standard library. There's probably someone who's debated putting it in the standard library, and there's a reason not. So they try to keep the standard library very dependency free. So there are obviously dependencies like OpenSSL or things like that. You can compile Crystal without OpenSSL if you want, but they try to keep it reduced, but they also do try to put as many dependencies or as many kind of libraries as you would want inside the standard library. Now, obviously, if you don't use it, the compiler just strips it all away. So you're not, if you do that puts hello world, you're not bringing in a lot of the other stuff that would be in the standard library. So it's, it's not free to put, good high-powered libraries in the standard library, but it's also, you don't always incur all the penalties because you're not having to load that inside the whole VM, basically.
There's some sort of requires that have to be made or something, I assume, to bring in the different standard libraries, or?
It depends. So they have the Prelude, which I think is a common pattern of making a lot of things in namespace. Just kind of, if you type in, HTTP or something, well, actually you have to require HTTP, but if you type in some things that just is inside the base namespace, that's the best way to put it. And then if you don't, some things require state. So, yeah. And they have been pretty good about going through the docs and making sure that any example that can be basically copy pasted into like a Crystal program. So they make sure to include requires and things like that. If you're going through the docs and it says required, it'll need it. But if it doesn't say required, most of the time it doesn't. So for the ecosystem, they have something called shards. It's kind of like bundler / gems, or NPM or something like that. So if you're looking for things in Crystal, shards is definitely kind of the tool you're going to use to kind of put together your project, build your project, get the dependencies, all that kind of stuff. It does have certain segments of programming kind of. It does have like the same parts that are in other languages. It has Camel and Amber for kind of web development. This is more of a Sinatra type framework. Amber is more Crystal, Rails. Camel, I think I like it better than Sinatra in a lot of the ways it does stuff. It's basically just a wrapper on top of the Crystal HTTP server in a lot of ways, because Crystal, parts of the standard library that went on there, Crystal just comes with WebSockets, like in the language. So when you talk about Sinatra and everything, or kind of the higher levels of that, the standard library in the language itself provides a lot of support for this kind of stuff. Amber is more like Rails. It's less developed than Rails, but it's still pretty good. I've written some projects in it and really enjoy it. They have ORMs like Granite and Clear. So if you're looking for more active record style, it's more Granite. Clear is kind of a mix of things, but it's definitely more of like an active. I don't know if I call it active style, but it's not the same as the kind of Ruby active record. It's inspired by other ORMs that have come around since then. So they definitely have a different, if you're looking for an ORM, if you're looking for a web framework, if you're looking for different things, they have a lot of stuff in the ecosystem already. And then also weirdly, there's like a kind of a language community inside Crystal. where there's definitely, if you look at Awesome Crystal, there's a handful of languages implemented in Crystal. And I don't entirely know why Crystal has become like a source or people are designing languages in Crystal, but it's pretty cool. Mint is like React, except for, it's compiled. It's got a lot of the advantages that you get from a compiler. It's, type checked and all that kind of stuff. And then Mist is kind of like, I call it Elixir in Crystal. It's a kind of functional. It's got a lot of pattern matching. It's got a ton of features that I think are like super awesome. I wish were in other languages and stuff like that, but they've basically implemented an interpreter and all this stuff on top of Crystal and implemented a very cool dynamic functional language. So, but there are more. There's a handful. So there's definitely the ecosystem is growing. It's not as developed as other ecosystems because it's just smaller. But there are definitely projects out there for anything we want to get into. There's probably someone who started something about it. So. And then we're coming towards the end, but I would not normally include C bindings as a reason to pick up a language. It's never been something I've really wanted to put inside my side projects before. But with Crystal, it's so stinking easy, and it's opened up so many possibilities that I've used inside personal projects. And I think it really shows the difference between VM-based languages, which I would never implement a C extension for inside Ruby just for a side project or something like that. Like it's too much work and it's not as fun. So this is what a C extension looks like in Crystal. This is void hello, takes a const char and prints out something. This is Crystal, you say link, and then you have a lib, and you say func, and then you put in Crystal types, and you just call it. And because it's a compiler, because it knows about header files and object files and shared objects and all that kind of stuff, it just compiles basically into your program, and you can put any C library basically into Crystal and just use it. There's a really cool C library that came out called H3. I've heard about it. I've not really used it yet. It's about like putting hexagons over like a sphere, like the globe, and then doing distances and stuff from Uber. And with this, you can grab the C code, put it on your computer, and just put lib, and then just call in whatever function you want for the library. You can even, this is maintained by the Crystal team, it'll turn a C library into a Crystal library. So anything that you want inside the ecosystem, like you can, the C ecosystem or that stuff, you can relatively easily turn it into Crystal code, and it's like, it's pretty cool, and it really opens up possibilities, especially for small languages. If your language is too small and there's a library you want to use to do, your project, and it's it's easy to bind. This makes it so easy to bind to if there are bindings for C. There are some like Ruby to Crystal stuff that is not as well supported anymore, but there's definitely interest in the community of kind of binding to different stuff, and I think is because it's LLVM, I think there's a lot of potential there to bind other libraries. And then lastly, performance. The order of magnitude is roughly Go, C++, Rust. We can debate about which one is more performant in that category, but we're talking in those kind of that range. And then it's definitely lower memory and faster execution speeds than Python and JavaScript and Ruby. I mean, it's just you're more on this side and less on this side. Here's just some benchmarks. I used Python because it was kind of faster across many categories. But Crystal's blue, Python's green. This execution time, so lower is better. We're talking about 400% increase when you use Crystal in a majority of cases, which is, machine code. It's running on the computer. Like if you run it through the LLVM optimizer a few times, even with GC and other stuff like that, you're just going to get faster execution times. So that's kind of the level that you're looking at, and obviously these will vary, but this is just kind of a general what to expect. And for memory usage, I was super surprised. Crystal does have GC, but I thought you'd see more in Python and stuff like that. Apparently GCs have gotten really good. You're looking at like a third of memory usage in a lot of cases. This is not a third, but this is JSON, so they're probably using some C library in Python. But if you look at a lot of, I think this one was the one that Google uses a lot, the NatMop. But generally you're going to have less memory usage on a lot of VM-based languages, but it's still GC, so you're still going to have some memory. And then we're going to start a Crystal meetup. I think we've basically nailed it down to the first Thursday of the month, which is coming up. It's at .org, which is unfortunately not up yet. Sorry for those of you that have a laptop. But we will be posting the meetup probably in the Slack channel in Chicago, in Crystal Lane and Ruby. Yeah.
Are you a street art enthusiast?
I guess so. Yeah.
I like that.
Okay.
Have you seen the Lego movie too?
No.
You should see it. It's fun. What's his name? Chris Pratt is the main character. He has to save the world.
Okay, cool. I'll definitely have to check it out. So we're doing a meetup here. I'm super excited about it. We're some, we might be partnering with the Rust kind of community in Chicago, and we're definitely getting its makers together, and we're going to try to kick that off next week. So if you're interested, please either contact me or look on the Chicago Tech Slack. Yeah.
Sorry, you about to say questions?
One second. I just wanted to wrap up. So wrap up. Ruby is, Crystal's very high level language inspired, very clean language inspired. Tries to give you abstractions that you can pierce all the way down to whatever kind of bits and bytes you want. It's all LLVM on the hood. Crystal is a very sophisticated, front end for LLVM. It's got a lot of semantics, but we get all the advantages of that. It's learned from a lot of languages. It's if you look through the issues, it's taken a lot of things that have come from Go or other communities, and it really lays them out to try to take the best solutions and take all the lessons learned. So they're very cognizant of everything that's come before them and also things that are going on now. And I think it's positioned well for future development. I think that we want OO languages. I think we want high-level languages, at least I do, to have a lot of really good abstractions for the projects I build in the future. But I also want a lot of the benefits of compilers, and I don't want stat typing to get in my way. And I think that LLVM-based languages and compiler ecosystem that's coming along is really positioned well for the next 10 years of language development, next 10 years of software development in general. So that's my pitch of where Crystal fits into the ecosystem as it is, the ecosystem where it's going, and why I think it's a really cool language. And now I'll take questions. Yeah.
So before you were talking about how if you have LLVM, then someone changes something in like Rust or any other language that is also able to compile to LLVM, and you're able to immediately get the benefit. You said a kind of complex sentence. Would you mind saying that sentence?
For sure. So anything that's if you're developing a language like Rust, or if you have people contributing back to LLVM, most of the people that contribute to Rust don't contribute directly back to LLVM, but as features are added to the ecosystem in general, anyone who uses LLVM can get the benefits from them. Crystal or these languages, in a sense, didn't write how to create certain create 64-bit support or add certain things into their languages. Like LLVM has that. And if you want both performance optimizations or kind of optimizations in kind of patterns or I guess they call them intrinsics, but the structures of a programming language, everyone else gets those benefits. So you get performance benefits, you get kind of all the benefits that hardware vendors and stuff are just having come up through the system. So does that make sense? Does that make more sense? So yeah, see some yeahs and some no's. So basically, because LLVM is kind of a language toolbox, if anyone adds support for a new feature in LLVM, all the languages get the benefits from it. Now, you're not getting benefits from syntax, you're not getting benefits from the semantics of your specific language, but you get the benefits of kind of building the building blocks of the language.
Yeah. Like LLVM could have a garbage collector implemented, let's say, and then a tool could use language to use that.
Yeah, they could. LLVM has stated in their documentation that they will not provide a garbage collector, from my understanding, but they provide hooks for it. So they specifically provide
Standard garbage collecting.
kind of stuff for that will so they're not going to implement GCs, they're not going to implement certain things, but if they, one of the things that was pretty interesting is a project of adding 128-bit integer support to Crystal. When I was reading about it, it said that most CPUs can do that in 2 cycles or a few instructions. So it's getting pretty quick even on ARM, but most CPUs can do it in 1. So if you use the LLVM's implementation of a lot of these things, you're just going to get a lot of benefits that it has across all the processors that all the targets it supports. And you have to know what 128-bit integer is inside your syntax, and then map it to an LLVM API, and then it will do all stuff back and forth. So I don't really know how hard it would be to add 64-bit support to a language, but after seeing some languages take so long to move from 32 to 64-bit support, a lot of the 64-bit support that we have in these languages comes from the compiler. So we don't have to add all that stuff in there. That's I don't really know kind of the depth it would take to kind of migrate the project forward, but you're getting a lot of the benefits of everyone kind of developing that inside the compiler. So, yeah.
Feel free to pass on this question if it's not your wheelhouse, but I've recently started working on a large Rails project and being similarly minded about static typing and wanting to have the compiler to have my back. Do you have any thoughts around Crystal's place in a budding ecosystem around optional type checking for Ruby and how it fits in?
My thoughts is that having it built in at the language level has made it really nice, and having it gradually has not worked out for me well in many projects. I've mostly used it in JavaScript and not gradual typing in Rust. But there's a thing where like if a library you bring in doesn't do it, then you just don't get it unless you go back and add it. So you can have kind of your core, your specific code written more type checked, which adds value. But then as soon as you hit a boundary of your code, you're really, kind of at the whim of whatever they did. And you can wrap your dependencies inside, kind of your own stuff and do checking and other things like that. But it depends on how defensive you want to get. I found gradual typing can be a benefit. I just haven't found it to be worth the effort in Ruby yet from kind of my playing around with it, but I haven't done anything big in it. Having it be a part of the language is really incredible, and it really, because most of us program with dependencies. There are dependency-free projects, but because of all of our, even the language itself that we're building on top of, or and all those standard libraries, or the dependencies we pull in, it's kind of getting, I think gradual typing in the Ruby ecosystem would be where we'd have to be at to really get a lot of the advantages of it. So,
have you heard of anyone like starting to rewrite Ruby code in Crystal and have like an interop layer between?
Yeah, I have. There are Ruby to Crystal projects. They have, because they use a lot of the more advanced kind of semantic projects, sometimes a Crystal version will break them, which is frustrating, but there has been some talk about including Ruby as kind of in the standard library for interop between them. I have to go back and read it. There are some people you can do the whole Ruby to Crystal interop inside a GIST. Like I've seen some people kind of do it inside one file type stuff, but it's definitely it hasn't been. A lot of people have talked about doing interops between Crystal and Ruby just kind of over time. I've seen it come back up in the community and inside the Gitter channels and inside people's GISTs and things like that. I think in the end, depends on what you're trying to do. If you want to write something in Crystal from the ground up, most people just end up rewriting or starting new projects in Crystal. And I think that if you want to do something in a Ruby project, HTTP, JSON has been the transport layer between doing stuff between them. I think that, what do you want from your Ruby projects in Crystal? If it's like a library that's specific to your business logic, there's probably a lot of benefit to not rewriting all your business logic and just calling into it. But I think, I've always wanted it because I've wanted certain things from old Ruby programs, but it hasn't kind of borne out to be as practical as I thought it would be. But there are certain ways you can do it. I kind of wish that there'd at least be some community kind of supported library for it, but it hasn't really been consistent enough in the zeitgeist to really get something going. So, yeah.
Interesting, it reminds me, the partial moving over projects reminds me of like TypeScript, like TypeScript. So it's like that people can kind of slowly migrate projects to be more typed and more typed and more typed using that. But
that was pretty interesting for a while. I thought that had a lot of good IDE or like support for editors and stuff like that.
Yeah.
And then Stripe released Stripe.
It's not out yet, but yeah, they have Sorbet, which is eventually going to be open sourced.
Yeah. There was another gradual typing system, I thought.
RDL is the one that Sorbet was kind of inspired by. That's out now, but I don't know how much production use there is on it.
Yeah, and I think it's also another interesting thing. Grace, a coworker of mine, we have a lot of documentation in our Rails project that specifically won't let certain APIs, like the documentation itself will prevent parameters and stuff that aren't documented and stuff like that. But so there's a lot of not type checking, but there's a lot of enforcement of certain documentation and things like that, kind of typing. And especially in Ruby, just the way the whole ecosystem works and the way that things kind of happen, like parameters and stuff are the best. You know, they're the cleanest interface to test, but it is really hard inside that environment to really get everything typed. And there's just so many things happening and so many dynamic things happening that I can't imagine trying to add types to all the object interfaces and stuff like that. It's just
The guys from Stripe did a really interesting talk at last year's Strange Loop where they talked about some of those challenges around like how do you static type something that's run within an instance eval context and knowing like, so they basically load the entire runtime and then export like all the, just basically do an object dump on everything and then get this, make everything statically checked from the types at runtime.
Yeah.
So making everything runtime now static, which is, yeah, that's really the only way. That's why I asked you that question about the method missing, because if you have that level of dynamism, you're kind of foregoing a lot of the static checking that a compiler grants you.
Yeah, it's really interesting, and like I would have checked the specific implementation of that, but that's my understanding of how it works, and that's the understanding of how a lot of other things in Crystal work. But it is, yeah, getting the like Ruby is amazing, and there's a lot of benefits to VMs that go beyond the ability that we couldn't implement this in GCC at the time. It just wasn't even an option, so we built a VM. Like VMs also manage certain things that are not as well managed or are not implemented in compiled languages. One of them is a runtime environment. You can build state, whether or not you like state, a runtime environment, and use that for branching and other things like that. So it is really cool. You can also do a lot of process management with VMs that I didn't really cover. It's way easier to set memory growth and memory caps in VMs, stuff like that. Even manage sort of the amount of forking it does or whatever. Like that's just all built in, and that's just part of the idea and design of it. And it's just not as much of the idea and design of certain compiled languages that I've seen. So, but yeah, the ability to kind of develop a Ruby environment and then being able to do things based on stuff is just easier because it's not just just a flat file of compiled code. But yeah. So, yeah. Any other questions? Any interest? I convince any of the crystals cool, but that should be yeah. Cool stuff. It's cool. Awesome. Yeah, I think it's cool. I think that these languages and crystals are my favorite of the next kind of batch of languages coming out are definitely showing a lot of advantages in the industry. I still think that so far for what I've seen, just as like a total side note, that compilers and memory management have been the biggest productivity gains of our industry that we've seen. This is not as big of a productivity gain, but it's definitely, I think it's definitely worth treating with a fair bit of optimism. So, thank you all.